Hi, everybody. I'm going to talk about some of the questions on this daily check just to make sure that, if you're struggling a little bit with this content, that you have a little bit of help on this nice eclipse day that we have going on. So this one here, right, this is just going to be a reminder of Lenz's law and trying to figure out also what these induced currents are proportional to. So here we have a rectangular loop of wire. It's being moved to the right with a constant velocity. A constant current I flows in the long straight wire in the direction shown. The current induced in the loop is, and as a hint here to this problem, the current I is this way. So if we use our right-hand rule, we see that the magnetic field is into the page. And remember that the way that the magnetic field works is that it's essentially a cylindrical symmetry around that wire. So if you have this, scenario where you have this into the page magnetic field, think about whether or not, as you move this loop, ask yourself, is the magnetic flux through the loop changing? And if it's not changing, what does that tell you about the induced current? For question 2, we now have the loop being moved the other way. The current's also slightly differently oriented, but the magnetic field, if you use your right-hand rule, you should be able to show the magnetic field is still into the page over in the area of the loop. And so when you think about this one, think about the case that the magnetic field over closer to the wire is going to be stronger, and over further from the wire, the magnetic field will be weaker. So as you're moving the loop away from the wire, is the magnetic flux increasing or decreasing? And what does the loop do to oppose this? So that'll give you a direction for it. And then whether or not it's proportional to I or proportional to I squared, let's just look at the fundamental equations. Remember that the magnetic field from a wire is equal to mu naught I over your 2 pi r, right? So the magnetic field from a long wire is mu naught I over 2 pi and the distance from the wire. So there's 1 I. And then if we look at the current induced in a loop, right? Remember that the induced current is going to be proportional to the induced EMF, which is negative n d flux dt. And that flux is just going to be equal to the integral of b dot dA. So there's 1b. The dA, the area vector, is not going to have any I in it, right? And so if you look, try to ask yourself, is there any other I? And if there's not any other I, then the induced current is just proportional to I. Okay, and then in this case, it's asking about the magnetic forces on the left-hand and right-hand sides of the loop. So just to clarify, it's saying over here, this would be my left-hand side, and then over here would be my right-hand side. So use your current from number 2, and then use that the force on a wire is IL cross B. And remember that my B was into the page because you're using the B from the wire. So that's the B from the wire. And then that'll give you, with your right-hand rule for the cross product, it'll give you what you need for this one. Here we have a copper bar in contact with a pair of parallel metal rails, and it's pulled up the page with a velocity v. So this is our induced EMF scenario. And so a uniform magnetic field is present pointing down into the page. So my B here, oh, sorry, not down, but actually literally downward like this. The bar, rails, and the resistor are all in the same plane. The induced current through the resistor is. So you have to then start thinking about whether or not there is induced current in this scenario. So do you have any change in your magnetic flux? So is there a change in your magnetic flux as the bar moves? Note that there's nothing into or out of the page. So if you don't have, remember, magnetic flux are field lines through a loop. So that should hopefully help you answer that. Okay, so for this one, we want to know that the magnetic field is increased by a factor of 2 magnetic energy density. So magnetic energy density, this is an equation from the previous videos where the magnetic energy density, so U sub B, the energy essentially contained in a magnetic field is equal to your 1/2 B squared over mu naught. So use that equation and you will be good to go. And question 6 gets to what we talked about in the video. The inductance of the inductor. Don't just use the equation. I'll say, see the video that I made. And is it a property of an object, or does it depend on the current? But look through the final derivation of it. Don't just look at that initial equation. Recall that for capacitance, C was equal to Q over V, which made it seem like C depended on Q and V. But C itself, when you went through that derivation, C was a property of the object. So look back at the video when I talked about the inductance of a solenoid, and you'll see what I mean about this question. Okay. Consider the circuit shown below. Which of the following statements most accurately describes the behavior of the system after the switch is closed? So the brightness of a light bulb is proportional to the power through the light bulb. So this is a recall question because this is a capacitor and this is my resistor, that light bulb. And when I first close the switch, right, and I have my source of EMF over here, then my current is going to flow until my capacitor is charged. And then at that point, it's going to be like an open circuit. So my current as a function of time here is going to decay downwards as a function of time. And the time constant here was RC. So let's find the answer that matches that. That's what you would do for this problem. Now for question 8, this is going to be like the video where we have an L and an R in series with an EMF. And just as a hint, this is the current rising phase. And I'll tell you then to see the video, or I also linked to the optional textbook if you wanted a quicker version of that. Just like in the normal modules, you have that option. Okay, so that just about does it for this daily check discussion. Good job, everybody.